Okay, so this presentation is going to be on the work we've been doing on the reconstruction of invisible flow fields of a transient natural convection system using a physics-informed neural network. And so to begin, we'll first kind of define what we mean by field reconstruction. So field reconstruction in the traditional sense, so let's say we have discrete measurements of velocity in a grid array from something like a PIV measurement, right? And so traditionally, what we mean by field reconstruction is, all right, I'm going to take some discrete field and then maybe reconstruct um, the continuous field, so going from a discrete case to a continuous case. Um, and so the way we're going to be talking about field reconstruction is the same thing, except we're going to go one step further. So taking maybe some discrete sparse temperature measurements, translating that into the full temperature field, and then going one step beyond and reconstructing the unseen velocity and pressure fields. So this is actually a very important area of study. So we're not always able to measure all of the fields with the highest fidelity. So maybe we're able to measure some temperature field with relatively good accuracy, but you know, simultaneous and synchronized measurements of temperature, pressure, and velocity is very difficult and very challenging in most cases. So we're trying to see, can we take some knowledge of my flow field, so I know that my flow is governed by continuity equations, conservation laws, and so forth. And with some data, am I able to reconstruct the full velocity, pressure, and temperature fields? Right? Okay, good. So, because this talk is more focused on machine learning, we're going to be just directly jumping into machine learning field reconstruction. So for now, we're going to be talking about non-physics based ones, so those that don't incorporate the knowledge of our governing equations. And so for most of these, it's done by fitting data to an output space. So kind of two examples here. The one on the left, we have an input of, let's see, the Reynolds number. H of t, that's the throat cross-sectional area, and then some pressure ratio, right? So going from that would be a 3D input space to the predictor results shown here. So they're actually predicting the air velocity within the nozzle itself. And here we already see some limitations of this, in that the output space here needs to be kind of a smaller tensor, if you will. So taking some CFD data, you need to first pre-process it into, in this case, it's a POD of the actual field itself, so a lower resolution of the actual field. And then the one on the right here is a mapping of upper and lower wall pressures to the output velocity. So this is looking at the velocity of a scramjet in the air at Mach 2.5. And here we kind of show one CFD result and one experimental-based results. But now we can see that in both cases here, we need to have a high amount of training data, basically, right? So either from simulations or from experiments. And so this is also a supervised learning task. So you have your input, so pressure and on the right, and Reynolds number and whatnot on the left there, right? So requiring a lot of data, and also when it comes to extrapolating outside of your training range, you really don't have much control on the outputs you would get from these models, right? So most of these models work great for interpolating within the input space that you've trained it on, but once you go outside of that, it's the outputs aren't really required to be confined to any sort of governing laws and so forth. So what people have done is, okay, given this plain neural network, am I able to augment some of the outputs and conform it to laws that we know govern our equations? So think your continuity laws and your conservation laws and so forth, right? So is there a way for me to morph my output manifold, if you will, to give me outputs that satisfies some properties that we want, like incompressibility and conservation of mass, conservation of energy, and so forth, right? And so, actually, PINNs itself has just recently been proposed in terms of the history of machine learning itself. And so, what smart people have done and found out was that in the calculation of backpropagation, we already find these partial derivative terms, and that's actually exactly what we need to calculate some of our PDEs, right? So here on the figure on the right, we're showing the calculation of incompressibility, of conservation of mass there. And so we see du dx and dv dy. Those are terms that we can calculate directly from backpropagation, and this can be put into our the loss function and update our network parameters so that our output space has a soft constraint on this continuity equation, and it kind of morphs and changes the output space to be all the possible solutions that satisfies this PDE, right? And so some applications of this is in simulating fluid dynamics, solving inverse problems. So as we've seen, as we said before, the going from one field reconstruction, that's a very hard inverse problem. There's with traditional methods, there's no really easy or even exact way for us to do that. But with a neural network, we're able to constrain the outputs into this multi-objective optimization problem and solve it that way. Okay, so using PINNs for reconstruction, we see that there's some advantages in doing this. We can reduce the data dependence. So maybe if we have sparse data, or even in some cases if we have no data, we can still do forward prediction. So meaning we go from the input to the output with full constraints on maybe the boundary initial conditions and so forth, right? And then we can also constrain the outputs to the physics laws with that PDE loss function. So I'll be showing the equations of loss functions later on, but we know now that we can constrain the physics law with doing backpropagation and finding those PDE terms. Okay. And lastly, we can also discover unseen fields. So what does this mean? When we build our PINN, we have the set of inputs, so that being spatial and temporal coordinates, and then our outputs can be basically whatever fields that we want to reconstruct. So in our case, maybe we look at pressure, temperature, and velocity, right? So given some temperature data, the PINN will have to produce some sort of velocity output as well. And the way PINN does that is it uses the PDE loss, and those equations are coupled. So we have temperature coupled with velocity and coupled with pressure, right, through conservation laws and so forth. And that's how PINNs can discover these unseen variable fields. And so some work that has been done on this before includes Rayleigh-Bernard convection. So we're looking at convection cells within a 3D domain, flows across a 2D cylinder. And then in this case here, the figures I'm showing is from this third paper here of 3D flow over an espresso cup. So the input here is some sparse temperature map, and then the output here we can see it's a more smooth and continuous temperature map. But also we can get the corresponding velocity map that accompanies this as well. But most of these studies looked at more or less a quasi-steady state phenomena, so not a lot of changes in time. And for a lot of applications, we actually want to have dramatic changes in time, and those are more interesting for us as engineers to look at. Right, so then the problem we chose here is a 2D transient natural convection in an enclosure. So more or less a canonical natural convection case here. We have heating on the left-hand side, cooling on the right-hand side, and we get this this clockwise circulation of flow that that circulates within our 2D domain, right? So we have buoyancy-driven flow on the left, and then it sinks back down from the constant lower temperature on the right-hand side. And here we're at a Reynolds number, at a Rayleigh number of 2 times 10 to the fifth, so still within the laminar regime. So making our jobs a little easier in terms of implementing those PDs in our pins. And then in our case, we're looking at the entire data set. So from t equals to 0, from our initial condition to mostly a steady state condition. So we're looking at our entire data set, so we can capture a lot of those high gradients in time data. Okay? And then in our case here, we're going to be taking some FEM data, so simulations from Fluent that we're using here. And then this is the temperature map with unknown velocity and unknown pressures, putting it into our PINN, and then reconstructing our fields as seen on this figure here. And so the research objective that we want to accomplish here is to understand the performance of PINN when reconstructing these highly transient convection cases. And so some questions that we would like to answer is that, okay, can PINNs reconstruct fields at arbitrary times? So what do I mean by this? So the figure on the top right here is shows this delta t with respect to time, so the temperature change with respect to time. And then here we see that we can set a reconstruction zone to be kind of arbitrary wherever we want. So we want to see, okay, if I place it closer to the initial conditions, or if I place it to the tail layer close to 60 seconds, what kind of behavior, what kind of errors can we expect from these regions here? So we defined kind of 3 different regions that we want to look at: the incipient phase, the development phase, and the quasi-steady phase, right? And that's characterized by these here. And it's kind of a general, not a very rigorous definition of these. And so at each stage, we want to look at how the errors are, and then what are the error sources. So where exactly are the problems arising from? And we know that these problems are inherently multiple scales. So we have a boundary layer and maybe the free stream region. So in these regions, do PINNs perform differently? And lastly, from all of these knowledge that we gain from doing this, is there a way for us to implement is there a way for us to improve the reconstruction accuracy of PINNs? Okay, good. So some equations here, we're looking at the 2D transient laminar flow with the Borznik's approximations. We're assuming that density change is only a function of temperature there. And then we're non-dimensionalizing and restricting the input and output range to be within 0 to 1, so a traditional normalization step for machine learning. And we also see that PD's stiffness can hinder optimization. So the stiffness of the PD is defined by, let's say if you have a very large term and a very small term of the PD, then those 2 terms would have very different step sizes. For those doing optimization, would be familiar with this. And lastly, we also homogenize the equations with the non-dimensional parameters. So some things we can do is maybe we can tune the reference length or the reference velocity so that most of these terms within our PDEs are of more or less a similar order of magnitudes. And so these PD equations are used to calculate the PD loss, and those are calculated at what we call collocation points as seen here. So we basically take a random sample of points within this 3D domain and calculate the PD losses at these points. So for the network architecture, we're using a 10 by 150 fully connected neural network with adaptive sign activation functions, which we've seen from prior literature review that these worked pretty well, so that's where we're implementing these. And so for our loss function here, we have the physical loss, data loss, and boundary loss. So physical loss from the PD, data loss from our temperature, and then boundary loss from our boundary conditions of velocity. And we find that equal weights for the composite loss function works just fine. And here we're showing that the middle figure here, we're just showing that the delta t, so the time steps, the step size of time for the boundary condition and data points can be different. And the figure on the far right here is just kind of a representative training iteration. So we're looking at the loss versus epoch here. Okay, so the results of PINN. So we're looking at the PINN reconstruction at various phases, so at time equals to 1, 20, and 50 seconds. You can see more or less it complies and agrees with the FVM results. But we can see that there are some errors in some areas. I have to go a little bit faster here to stay within time limits. So now we look at the temporal gradient and the solution space. So we define the solution space of PINN to be the range of possible field distributions that the PINN can converge to. So it's kind of analogous to thinking about the degree of freedom of our output space. And then here we define the incipient, development, and steady state phases here. And the figure on the bottom left here shows the error of the x velocity at time equals to 10 and 50, and we see that at time equals to 10 we have a larger error. And the figure on the right here shows the error versus time, and then also the gradient of the velocity. So we see that gradient velocity starts out high and then decreases, and then we see the error there. Okay, so for spatial gradients, and then we're going to be looking at vanishing gradients as well. So vanishing gradient is the phenomenon where repeated multiplications of small gradient eventually leads to extremely small gradients that contributes nothing to the optimization step. So think you're multiplying everything by 0 essentially, and then your update step doesn't really update anything at that point. And so here we kind of map out the spatial gradients, and it seems like it's an intuitive way of visualizing the vanishing gradient cases. So here we're plotting these on 10 to the negative 6 to 10 to the negative 2, so order of 10 to the 4. And then here we're plotting the temperature and x velocity gradient fields here. And we see that the higher error occurs near areas of small gradients. And so now we've seen that the scale of the output space actually does matter to the performance of the PINN. And so we do the multiple scale analysis to see is there a way for us to implement the scaling information into our PINN itself. And so from perturbation methods, we want to basically say that we want the PINN to have a uniformly valid approximation across all inputs. So meaning if my x is small and versus my x is large, the validity of the PINN should be the same. And this arises from analysis of the asymptotic expansion. And this is sort of similar to a Taylor series expansion, but in this case we're actually doing an asymptotic expansion, meaning the first term should be order of magnitude larger than the second and the third and so forth. And from that analysis we see that with these PDEs we get these secular terms that arise, so meaning at certain regions of our input the first order term and the second order term actually becomes the same order of magnitude, and that completely breaks the asymptotic expansion that we expect. And so now we assume that the PINN solution is made up of small and large scales that dominate in different regimes. So for example, we say the u velocity is now a function of x and x over epsilon, where epsilon is small. And so now we see that when x is small, or of the order of epsilon, with that second term there is of order 1 and would contribute to the u. And when x is of order 1, that first term there would contribute to u. And so now we modify our inputs to be this augmented input that takes into account the scaling information, and we can still use the traditional backpropagation step all the way back to our input and calculate our PDE loss exactly the same way. And so now we show some of the results of MS PINN versus the traditional PINN. So we see an improvement in both the mean and maximum error there. And we see that there's higher error reduction near earlier frames and near intersections of boundaries with the free stream itself. And also we see a higher performance gain for sets 2 and 3 labeled at the top right there. So that's a transition between, let's say, the incipient and the development phase. And so we also look at the spatial error distribution of the PINN versus the MS PINN. So we see the error reduction in small gradient regions, and we also see that the error structure or the shape of these regions stay relatively unchanged. And here we show the reconstruction error at 1 second, 20, and 50 seconds, again to kind of encapsulate the errors in these three regimes that we're looking at. And so, in conclusion, the errors attributed are attributed to spatial and temporal sources. So large solution space, think higher gradient in terms of time, increases error, and we also see that small spatial gradients lead to that vanishing gradient term, and that also increases error. And we also see that the rescaled PINN is able to outperform the normal PINN with the mean and max improvements shown here. And further validation is still needed for different flow conditions, of course, and experimental data. And these are ongoing work in our lab. And for more detail, I would recommend looking at the preprint that we have in arXiv right now. So with that, I would like to close and open up this for any questions.